Hello friends, so this is part 2 for the year 2021, and in this part 2 we are going to solve 11 questions. And these 11 questions are from the mains. In part 1 also we solved questions from the year 2021, and that were consisting of 10 questions. In the first question, it states that two electrons each are fixed at a distance 2d. A third charge, proton, placed at the midpoint is displaced slightly by a distance x such that x is very much lesser than d. Perpendicular line joining the two fixed charges. Proton will execute simple harmonic motion having an angular frequency, and m is the mass of the charged particle. So we are supposed to find out the angular frequency of the SHM. So we can draw the basic figure for that. We are given that we are having two charges, and this is our first electron, second electron, and the total distance between the two is our 2d. A proton is placed at the midpoint and it is displaced by a distance of x, perpendicular line joining. So it is displaced by a distance of x. So let us suppose this is our distance x by which it is displaced, and this is our proton. And we can assume that the initial position of the proton, let us suppose, is the origin. Coordinate will be 0, 0. So on the left side we are going to have this as minus d, 0, and the right side we can say it will be plus d, 0. So we can just join this point P and other end, and let us call this as A, B, and the origin as O. And there will be force. We can assume that it is a making angle of theta with the radius vector, or we can say distance vector, and the force of attraction will be along the line, and similarly to the other side also. And if this angle is theta, so obviously we are going to have this angle with theta. So we can divide our F, let us suppose this is our force F, into two components. This will be F cos of theta, other side will be also our F cos of theta, and toward the origin, which will be basically acting as a restoring force, will be giving us F sine of theta, and the other will be also our F sine of theta. Our these horizontal forces, that F cos of theta and F cos theta, are going to balance each other. So net force will be acting along the y-axis, and we can say that will be equal to 2F sine of theta. And the position of the proton we can say is our 0, x. So let us suppose this distance is given as r, and similarly to the other side this distance will be also r. So the net restoring force that will be acting in the y direction, or first of all let us find out our force due to one electron. Force due to one electron that is our F will be equal to, we have this as 1 upon 4 pi epsilon naught E square upon R square. R square will be equal to D square. This distance will be our D, and we already know this distance is our X. So here R will be equal to our X square plus D square and its square root, okay, on the both sides. X square plus D square and its square root. Therefore, we can say our force F will be equal to 1 upon 4 pi epsilon naught E square, and this comes as our R square plus X square. And only vertical component is going to contribute to the restoring force. You can say that only vertical component contribute to the restoring force. Restoring force. So we can say that will be our, suppose, F of y, and that will be equal to our F cos of, F sine of theta. And we can substitute value of F as well as sine of theta. So F was our, let me write it F, and this comes as X upon D square upon X square and its square root. And we are given that our X is very much smaller than D. Therefore, we can write that our F of y will be equal to, if we substitute value of F, we get this as 1 upon 4 pi epsilon naught E square divided by R square plus, not R square, but D square. D square. And here also our D square X square, and this comes as X upon D square plus X square and its square root. So according to the condition that X is very much smaller than D, we can write that this will be equal to our 1 upon 4 pi epsilon naught E square upon D square multiplied by X upon D. So we get this as F of y is equal to 1 upon 4 pi epsilon naught, and here we have our E square X upon D cube. Now this is the restoring force only because of one electron, but we have 2 electrons. Therefore, you can write that net vertical restoring force, net vertical restoring force, let us suppose that is of F net along y axis will be equal to 2 times F of y. So we substitute F of y, we get this as F net along y axis will be equal to, this comes as about 2 times 1 upon 4 pi epsilon naught E square X upon D cube, and here 4 goes by 2, so we are left with this as 1 upon 2 pi epsilon naught E square D cube and multiply by X. And this is our, you can say, and this, the net force is along y-axis, or we can say that it will be in the negative y direction, okay, because this is x-axis, and if we go move upward we are going to get positive of y, and if we go downward we are going to get minus of y. So we can simply substitute here minus. Therefore we can write that restoring force, that is of F net comma y, is proportional to the negative of the displacement. So we can make a comparison of this with the standard equation, which gives us the restoring force F R in general is equal to m omega square times x, and which sometimes this particular is sometimes also written as k effective, which you can write minus k effective times x, but we are supposed to find out the angular frequency. So if we make 1:1 comparison between the two equations, we get that our m omega square is equal to 1 upon 2 pi epsilon naught e square divided by d cube. So from here we get our omega will be equal to e square divided by, this comes as 2 pi epsilon naught m d cube and its square root. So this is the our angular frequency. And option, okay, in spite of E, it is written as Q, so this we can just generalize it in form of Q also, that doesn't matter, so we can write this as Q. Here our E is nothing but our Q, so we get Q square 2 pi epsilon naught, and option number 1 is correct. Option 1 is correct. Next question. We are given a point charge of 12 microcoulomb is at a distance of 6 cm vertically above the center of a square of side 12 cm as shown in the figure. The magnitude of the electric flux through the square will be dash 10 to the power 3 Newton meter square per coulomb. Basic figure is given to us. We are given a square which is 12 by 12, and charge of plus q is placed at a distance of x from the center of the square. And we are going to use here Gauss law, but the important part in Gauss law is that the charge should be always enclosed. Okay. So we have our Gauss law, which states that the flux total associated with the enclosed surface is basically a charge enclosed and divided by epsilon naught. So which basically means that this given charge q should be enclosed in a surface. So in order to enclose this surface, we are going to draw a cube whose base will be acting the given square. Okay. And this is the cube, so height of that cube will be coming as 12 centimeter. So this particular charge will be exactly at the center of the cube. So we can just draw the cube. And the basic surface that is given to us is this one. And it is a 12 by 12. So this is a 12, this is 12. So obviously this side will be also 12. Okay, so let me name this is A, B, C and D. Therefore we can say this is our A, B, C and D. From the center we are having the charge is placed at a distance of 6 centimeters. So this is our charge placed as plus Q. Okay, now the charge is enclosed inside a cube. Okay. So we can say that the charge Q should be enclosed. Therefore, drawing a cube with base as the given square. Given square, and given square is our A, B, C and D. And because of this we can say from here that the charge, point charge which basically means that given charge is at the center of the cube because of the height, because this height is our 6 and the entire length of this cube is our height of this cube is our 12. So this charge will be entirely exactly at the center. And please remember this cube is, we can solve this cube is our imaginary cube, doesn't, so this is our imaginary cube. Okay, therefore the flux will be symmetrically distributed along all the faces because it is symmetrical exactly at the center. Therefore we can say that since the charge is at the center, the electric field lines are symmetrically distributed through all 6 faces. Through all 6 faces of cube. Therefore, we are interested in only one side, that is one face, that is A, B, C, D. Therefore, we can say that electric flux through one face, that is basically given square, and that face is our A, B, C, D, will be equal to phi of square is equal to 1 by 6 Q upon epsilon naught. And values are given to us, we simply substitute the values. we get this as 1 by 6. Charge is over 12 into 10 to the power minus 6, and epsilon naught is over 8.85 into 10 to the power minus 12. So this gives us flux associated with the square phase is equal to 2 to 6 into 10 to the power 3. Therefore, the value is, our answer is 2 to 6 into 10 to the power 3. Next question. We are given two equal capacitors are first connected in series and then in parallel. The ratio of the equivalent capacities in the two cases will be. So this is quite simple. We have two equal capacitors. Okay. So let us suppose we have two capacitors. First they are connected in series. Let us suppose capacitance is C1 and C2, and then they are connected in parallel. C1 and C2. So when they are in series, so you can say series connection. The equivalent capacitance let us suppose that is given as CS, and the CS, sorry, not CS but 1 upon CS will be equal to 1 upon C1 plus 1 upon C2. Both are same, so we get 1 upon C plus 1 upon C, which gives us that our series will be equal to C upon 2. Now we have a parallel connection. And equivalent capacitance let us suppose we get this as CP, then our CP will be equal to C1 plus C2, which comes as C plus C, giving us 2C. So we have our CP as well as CS. We need to find out the ratio. So we get this as our CP upon CS will be equal to 2C upon C upon 2. C and C cancels out, and this comes as 4:1. So option 3 is the correct one. One second. First series, okay. This has to be reverse. My mistake. So this comes as 4, and we need to this as series to parallel, which comes as 1:4. Because first they are connected in series, then they are connected in parallel. So the option 2 is correct. Correct. Next question. We are given a cube of side A has a point charge is plus Q located at each of its vertices except at the origin, where the charge is minus Q. The electric field at the center of the cube is. So we have to find out the electric field at the center of the cube, which we can say is something here. Okay. And we have all the charges at the vertices are positive except at the origin, that is minus Q. So we can write that there are total 7 vertices. Sorry, total are 8 vertices, but we have charges of plus q. There are at 7 vertices, and charge of minus q, it is at origin, or we can say at one vertex. So we can just write the coordinates of the cube, and we can say that the coordinates of the cube vertices rather coordinates of cube vertices, and the vertices will be our 0, 0, that will be origin, and then we start with a 0, 0, and we have this as 0, a 0, and we have this 0, 0, a. Then we can have our a, 0, this is a 0, a, and we have this 0, a, and we are having this is a, a. So at the origin we are having a charge of minus q, and everywhere rest we have charge of plus q. Plus q. So we have to find out the net electric field at the center of the cube. So we can find out the position of the center of the cube. Position of center of cube and let us call this as our R center, which will be giving us a by 2, a by 2 and a by 2. And we know the general formula that electric field at point R due to a charge q whose position vector is suppose rq, because it is a relative concept here, so we are going to use the relative position of the charge also. So we can say that electric field at point R due to a charge q due to a charge q at position rq, and this is given as electric field is equal to 1 upon 4 pi epsilon naught, and we have this as q times, and this will be r minus rp divided by r minus rp and its magnitude whole cube. And we are going to use this formula for all the 8 charges and do the vector addition. And instead of calculating for 8 vectors, because this cube is symmetric and the center point is symmetric, so we can use the symmetricity in order to find out the value of this R as well as our RP. So we can say that each charge lies at the vertex of the cube. At the vertex of the cube, equidistant from the center. Equidistant from the center. Therefore, the side of the cube is given as A. So we can write the distance from center to each vertex. The distance from center to each vertex. Let us suppose that distance is given as capital R. Therefore, we can write capital R will be equal to A by 2 whole square plus A by 2 whole square plus A by 2 whole square and its square root. This gives us A root 3 divided by 2. And for each vertex which is having a charge, we are going to generalize the formula, and that it will be much more convenient to write the solution. So we can say that for each vertex charge, let us say this is our Q of I at a distance of R of I, the field at the center. The field at the center. And we can write this as our E of I will be equal to 1 upon 4 pi epsilon naught, and this we have our Q of I, and this is our RC minus R of I and divided by our R cube. Now here value of I is going to vary from 1 to 8. Okay. I is a representation of number of charges. Now we can easily find out the net electric field. So net field, and we are having 7 charges which will be plus Q, and we are having 1 charge that is of minus Q. So we can expand the given formula, or this formula equation 1, we can say that the field due to 8 charges field due to 8 charges, this is our E net, will be equal to summation of from I to 8 1 upon 4 pi epsilon naught, where this have Q of I dot R of I unit vector divided by R square, because they are at the same distance. Okay, and so the field will be directed from the charge to the center, except the negative part. Therefore, we can just elaborate the formula, and so we can further write this as our electric field will be equal to total charge Q divided by 4 pi epsilon naught r square, and we have here summation of I 1 to 7 r unit vector minus our r naught unit vector. And here our Ri unit vector, it is a unit vector from the vertex to the center, and this is for the positive charge. So we can say unit vector from vertex I to center, and this is because of the positive charge. And our second, that is of R naught, is same, but it is due to negative charge. We are having only one negative charge, and we are having total 7 positive charge. So we can easily calculate this first part because of the symmetrical. We can say that our due to cube symmetry, the sum of all the unit vector is equal to 0. Due to symmetry, the sum of all unit vectors from each vertex to the center is 0. And mathematically we can write that we need that this sum should be equal to 0. Therefore, we can write that our summation of our I 1 to 7, and this we having our Ri unit vector should be equal to minus of R unit vector. Then only this summation is to be 0. So substitute it, we get our electric field will be equal to Q upon 4 pi epsilon naught minus R naught unit vector minus R naught unit vector. This will be giving us minus 2Q divided by 4 pi epsilon naught, R square, and we have this is R naught unit vector. And we need to find out here R naught unit vector, which we can find out easily. Our R naught unit vector will be a by 2 comma a by 2 comma a by 2, and this whole divided by r vector, r, and this can be written as 1 by 3 square root, and we have our I plus j plus k. We substitute value of r unit vector, we get this as our net electric field will be equal to minus 2q divided by 4 pi epsilon naught, and we have r square multiply by 1 by root 3 and I unit vector, j unit vector and k unit vector. We already know that our r is equal to a root 3 by 2. So from here we are required r square will be giving us 3a square by 4. So we get our electric field will be equal to, this is minus, this is come as 2q 4 pi epsilon naught, and we have here 3a square by 4 multiply by square root of 3 I unit vector, j unit vector and k unit vector. And let me check what is the answer given. We can just modulate it. Okay, 4 and 4 is cancels out, 4 is not present. So here 4 and 4 cancels out. So we get our electric field is equal to, this is minus 2q and we have this as 3 root 3 and pi epsilon naught a square I plus j plus k unit vector. So this is our electric field at the center, and option number 3 will be the correct option. Option 3 is correct. Next question. We are given that an infinite number of charges, each of charge 1 microcoulomb, are placed on x-axis with the coordinates x equal to 1, 2, 4, 8 and infinity. The total force on 1 coulomb point charge placed at origin is x into 10 to the power 3 Newton. The value of x to the nearest integer is. So we are given that the charges are placed along x-axis, and suppose this is the origin, and we have a charge of total force. Okay, so 1 coulomb charge is placed at the origin. So this is the charge of 1 coulomb, and 1 microcoulomb are placed at a distance of, suppose this is our q1, q2, q3, q4 and up till infinity, and these positions are given as 1, 2, 4, 8 and so on. And we have to find out the total force at origin. So this is our origin. Basic formula of the force, we know that our force between 2 point charges between 2 point charges, that is a F, will be equal to, we have this as K Q1 Q2 upon R square, where R is the distance of origin to each charge, and all the charges are positive, so there will be a repulsive force between them. Okay, and we are having 1 coulomb will be the higher side, so all the charges will be applying a net force toward the positive x-axis. So the distance with respect to the origin, for the first charge it will be 1, for the second charge it will be 2, for the third charge it will be 4 and so on. And we can write the general expression for the R, because R the distance between the point charges, and we can say that the position of the charges distribution of charges, which is our suppose R of n, because it is up till infinity, and we can write this will be equal to our 2 raised to power n minus 1, where value of n will be equal to 1, 2, 3 and so on. Okay. Because value of n is 1, so this comes at 2 raised to power 0, so we get first value 1. Second value of n is 2, 2 minus 1 we get this is 2. Third is our 3, so this comes as 3 minus 1 will be 2, so this comes as 4 and so on. Therefore, we can write, or we can also generalize the given force formula. So we can say that the force on 1 coulomb charge due to each 1 microcoulomb charge we can write this will be equal to over f of n will be equal to k times charges are 1 into 1 into 10 to the power minus 6, and value of r is our 2 raised to the power n minus 1, and this comes as whole square, which we can write k, this 10 to the power minus 6 divided by this will be 4 raised to the power n minus 1, and value of n is from 1 to infinity, so we can just make a summation of that. We can say total force, let us suppose that is given as F, will be equal to, we can take 10 to the power, we can take k into 10 to the power minus 6 is common, this will be summation 1 upon 4 raised to the power n minus 1, and it goes from n1 to infinity. And we can make a minor adjustment here, we can write this as k 10 to the power minus 6, and this comes as summation from n0 to infinity, and we are left with 1 upon 4, and this comes as our raised to the power n. This is basically our geometric series. So we are interested in this particular solution, so we can write this as summation n is equal to 0 to infinity 1 upon 4 raised to the power n. It will be coming as 1 upon 1 minus 1 upon 4, which will be equal to our 4 by 3. So we substitute it, we get our f is equal to value of k we already know is our 9 into 10 to the power 9 multiplied by 10 to the power minus 6 multiplied by 4 by 3. Here 9 goes by 3, so we get this as 12 into 10 to the power 3 Newton, and so value of x is equal to over 12. So this is the value of x which we are supposed to find out. Next question. It states that an oil drop of radius 2 mm with a density of 3 gram per centimeter cube is held stationary under a constant electric field 3.55 into 10 raised to the power 5 volt per meter in the milkman's oil drop experiment. What is the number of excess electron that the oil drop will possess? Consider G as 9.8. So here there will be two forces. One will be because of the electric field, and other force will be because of the mg, that is weight, and it is stationary. So we can say electric force is equal to our mg, which is basically the gravitational force. So we can say For equilibrium, electric force is equal to gravitational force. So we can say Q multiplied by electric field is equal to our mg, and Q is our charge, and we can write this as n multiplied by electron. N is the number of electrons. So we can write further it as n times E multiplied by electric field is equal to mg. We have to find out value of n, and we also need mass, so we can easily find out mass will be equal to our volume time density. So this comes as 4 by 3 pi r cube multiplied by density, and radius is given to us as 2 millimeter. Therefore we can write that our mass is equal to 4 by 3 pi r cube is our 2 into 10 to the power minus 3 whole cube multiplied by 3 into 10 to the power 3, which gives us that value of mass will be approximately equal to 1.005 into 10 to the power minus 4 kg. So we need to find out value of n, and so we can say that our n is equal to our mg divided by charge on electron multiplied by electric field. Mass we just found out, we substitute value, we get this as 1.005 into 10 to the power minus 4, g is 9.81, 1.6 into 10 to the power minus 19, and electric field is given to us as 3.55 into 10 to the power 5. So we get that the number of electrons will be equal to 1.74 into 10 to the power 10. So we have this as 1.73 10 to the power 10. So option 2 is correct. Correct. Next question. We are given a parallel plate capacitor has a plate area 100 meter square and the plate separation of 10 meter. The space between the plates is filled up to a thickness of 5 meter with the material of dielectric constant 10. The resultant capacitance of the system is is x picofarad. The value of epsilon naught is 8.85 into 10 to the power minus 12. The value of x to the nearest integer is. So here we are given that we have a capacitor, parallel plate capacitor, and whose area is suppose A, and D is the distance between the plates, which is given to us at 10 meter. Now within this plates we put a dielectric and thickness is 5. So obviously it will be exactly to the half of that plate. So this is a dielectric. So we are going to get this will be our d by 2, and here also our d by 2. Therefore we get two capacitors now. One is suppose our C1 with dielectric is air, and another one is C2 with dielectric, let us suppose constant is given as K and value of K is given to as 10. Now these two capacitors will be in series now. So we can say that After the insertion of dielectric, there are two capacitors C1 and C2 in series. We have capacitor C1. Area in both the cases is same, that is our A. We have capacitor C1 and which is having a thickness of d/2, which will be obviously equal to 5 meter, and air as dielectric. Whose dielectric constant is equal to 1. Then we have our C2 and whose thickness is also our d/2, but the with dielectric, and its dielectric constant is K. Value is given to us as 10. So we can find out the equivalent capacitance. Let us suppose we call this as C equivalent. Then we get 1 upon C equivalent will be equal to 1 upon C1 plus 1 upon C2. C1 is our with air, so we can write this as 1 upon C equivalent is equal to 1 upon epsilon A and divided by d/2 plus, and we get this as C2 will be equal to 1 upon K is a dielectric constant epsilon A divided by d/2, and d/2 we know is a 5. Therefore we can say that our d/2 is a 5, epsilon naught, let me take them as common, much more easier. We get this as 1 upon epsilon A d/2 is common, so we get this as 1 plus 1 upon K, and we are just substitute the values. We get this as 1 upon C equivalent is equal to d/2 is our 5, epsilon is our 8.85 into 10 to the power minus 12, area is given as 100, 1 plus, and this we are having as 1 upon 10. So this comes as 5 upon 8.85 into 10 to the power minus 10 multiply by this will be coming as 11 by 10. So we get our C equivalent will be equal to this will be our 8.85 into 10 to the power minus 9 and divided by 55, which we can say is approximately equal to 161 picofarad. So this is 161 picofarad, because required 2 in picofarad. Next question. We are given the electric field in the region is given as 2 E naught I divided by 5 and 3 E naught J divided by 5, with E naught is equal to 4 into 10 to the power 3 Newton Coulomb. The flux through this field, the flux of this field through a rectangular surface of 0.4 meter square parallel to YZ plane is. Okay, so we are given electric field, and the equation of electric field is our 2 by 5 E naught I unit vector plus 3 by 5 E naught J unit vector. Value of E naught is our given to us as 4 into 10 to the power 3. Surface area A is also given 0.4 meter square, but it is given that it is parallel to YZ plane, and in order to find out the flux, we should be knowing the unit vector that will be associated with our area vector. Okay, so we can easily find out that we are given that the surface is parallel to YZ plane. Therefore, we can say the normal vector and suppose that is n unit vector to this surface is along x-axis. Or which we can say that our n unit vector is nothing but our I unit vector. Therefore, we can say that electric field or we need to find out the flux. Let me write the formula of flux, then we can calculate of electric field. Therefore, we can say electric flux phi will be equal to our E dot n unit vector and multiply by area vector. So we already know our electric field is given to us as 2 by 5 E naught I unit vector plus 3 by 5 E naught J unit vector dot n unit vector is our I unit vector, and this is whole multiplied by the area vector, which is our 0.4, and this dot product of I and j will be coming 0, so we are left with only I dot I, which will be equal to our 1, and that will be coming as 2 by 5 E naught is given to us. E naught is our 4 into 10 to the power 3. 4 into 10 to the power 3, area vector is 0.4. Therefore, we get our flux phi will be equal to, this will be 8 divided by 5, 8 divided by 40, 8000 divided by 40, and 8000 divided by 50. Now, one second. This is 8, 8, and 32 divided by 50, and it means 32,000 divided by 50, which will be coming as 640 Newton meter square per coulomb. So this is our value of the flux, which is our 640. Next question. We are given a 2 microfarad capacitor C1 is first charged to the potential of 10 volt using a battery. Then the battery is removed and the capacitor is connected to an uncharged capacitor C2 of 8 microfarad. The charge on C2 on equilibrium condition is dashed microfarad. Round off to the nearest integer. Basic figure is given to us. We have two switches, S1 and S2. So first S1 is closed and this C1 is charged with the to the potential of 10 volt. Then our S1 is opened and our S2 is closed. So as soon as S1 is opened, battery is removed from the circuit and we have these two capacitors connected with each other. And then we have to find out what will be the charge on C2. C2 is initially uncharged. So as the battery is removed, so here we can use that total charge before and after is going to remain same. So let's find out the initial charge on C1. Initial charge on C1, let us call that Q1 will be equal to C1 V1. Okay, and let us call this C1 multiplied by V. This is our V. Therefore, we can write our Q1. C1 is our 2 multiplied by 10. This gives us 20 microcoulomb. And when battery is removed, the charge is going to redistribute among itself because both the capacitor will try to come to a common potential. So you can say when C1 and C2 are connected, C1 and C2 are connected, battery is removed. Battery is removed. So therefore we can say charge redistribute. Charge redistributes. And we can also say that the total charge is conserved. Total charge is conserved. Initial charge on C2 is equal to 0. So total initial charge is our 20 microfarad. So we can say total initial charge is, let us suppose our Qt will be equal to our Q1, that is our 20 microcoulomb. And because of conservation, this will be equal to total final charge. Total final charge. How much it is going to distribute among C1 and C2, that is not required, so we are not going to find it. But its value will be, total value will be equal to 20 microcoulomb. Therefore, now both C1 and C2 are in parallel. C1 and C2 are in parallel. Therefore, we can find out equivalent capacitance. Let us suppose that is our C will be equal to C1 plus C2. Value are given to us 2 plus 8, giving us 10 microfarad. And they should be at the same potential, both the capacitors. So you can say final voltage across both capacitors should be same. Because they are connected in parallel. Let us suppose that final voltage of Vf, which will be equal to our total charge Qt divided by our C equivalent, that is our C. Let me write this C equivalent. Total charge is given as 20 microcoulomb and we found out C equivalent is 10 microfarad. Therefore, we can say our final voltage will be equal to 2 volt. And we need to find out the charge on C2. Okay. So this is the final voltage. So which basically means that the voltage across C1 will be our 2 volt, as well as voltage across C2 will be also our 2 volt. Now we can just find out the charge on C2. Charge on C2, let us call this as Q2 prime rather, and that will equal to C2 multiplied by voltage across capacitor C2, or we can say also we can call this term as our Vf because it is same. C2 is our 8 multiplied by 2, which gives us 16 microcoulomb. So we get this as value will be equal to 16. Next question. We are given 4 identical electronic plates with length 2 cm and breadth 3 by 2 cm are arranged as shown in figure. The equivalent capacitance between A and C is X times epsilon naught divided by D. The value of X is round off to the nearest integer. Here we are given 4 plates, plate A, B, C and D. Plate B and D are connected with each other. Okay. Or we can say they should be at the same potential. Plates B and D are connected. So which means they are at same potential. So let us assume that the capacitance between A and B is called C1, capacitance between B and C is called C2, and capacitance between C and D is called as C3. Area of the plates is same for all and distance between the plates is also same. So we say between A and B, capacitance C1 will be equal to epsilon naught A upon D. Between B and C, C2 will be also epsilon naught A upon D, and between C and D we have C3, that is also epsilon naught A upon D. And we need to find out the effective capacitance between A and C. So we have to form the equivalent figure for the given circuit. And let us start with point A. So this is point A, and point A and point B. So this is point B, and point B and point D are common. So let us call this common point as X. Okay. And then we are having between point B and D that is common. One is our C, and second one is between C and D. Okay. So this is between C and D, and we have this common node at X. This here is C and D common point. Okay, so this will be our between A and B we are having C1, between B and C we are having C2, and between C and D we are having our C3. So this is the equivalent circuit of the given circuit. So we get C2 and C3 will be parallel, so we can find out the equivalent capacitance, and the circuit will be coming something like this. This is our C1, and this is our point X, and this is our C equivalent. We can just find out their value. This is A and this is our C. So we can write our C equivalent, parallel combination of C2 and C3, which comes as C2 plus C3. We already know there this is epsilon naught A upon D plus epsilon naught A upon D, giving us twice epsilon naught A upon D. And this C1 and C equivalent are in series. So we can find out their, this is point A and this is point C. Let us call this equivalence capacitance as C equivalent prime. Now let us call this as prime, and this is normal. Therefore we can say our C equivalent will, these are in series. Therefore we can say 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C equivalent prime, and we get this as epsilon naught A upon D plus 1 upon 2 epsilon naught A upon D. We can just further write it as D epsilon naught A plus D upon 2 epsilon naught A, and we can take this as common, or we can just add them. We get 1 upon C equivalent is equal to, this comes as 1 plus 1 by 2, which comes as 3 by 2. So this will be our 3D divided by 2 epsilon naught A. So we get our C equivalent will be equal to 2 epsilon naught A divided by 3D. A is the area, so we can just find out area will be equal to our 2 into 3 by 2. This 2 and 2 cancels out, so we get area is equal to 3, and value of D is given to us as, okay, it is compared, no problem. So we can say that our C equivalent is equal to, this comes as area is 2 multiplied by 3 divided by 3, and we are having this as epsilon naught upon D. 3 and 3 cancels out, so this comes as our 2 multiplied by epsilon naught D, which is given as X epsilon naught upon D. Therefore we can say value of X is equal to 2. The value of X is our 2. Next question. It states that a parallel plate capacitor whose capacitance C is 14 picofarad is charged by a battery to a potential difference V 12 volt between its plates. The charging battery is now disconnected and a porcelain plate with K7 is inserted between the plates. Then the plate would oscillate back and forth between the plates with a constant mechanical energy of dash picojoules. So here also we are having a parallel plate capacitor and capacitance is given as C, and it is connected to a supply of 12 volt. Let us suppose that is our V. And when the battery is disconnected, a porcelain plate, its thickness is not mentioned, so we can assume that it is very thin, is inserted between the plates, and its dielectric constant is given as 7. And it says that it oscillates back and forth between the plates and battery is removed. Okay, so here charge is going to remain constant because battery is disconnected. So let's find out charge before the insertion of plates. Let's suppose that charge is given as Q. So we can see our Q is equal to C times V, which we have our 14 10 to the power minus 12 multiplied by 12. So we get our Q will be equal to 168 into 10 to the power minus 12 coulomb. So this is the charge before the insertion of the plate. And from here we can also find out the energy. So we can say energy before insertion of plate energy before insertion of plate, let us call this as UI, will be equal to half CV square, and values are known to us. We can say our U of I will be equal to half 14, and we have this as 12 square, 14 into 10 to the power minus 12, and this is our voltage is given to us as capacitance is 14, voltage 12. Okay, so this comes as 12 times whole square. So we get our initial energy will be equal to 1008 into 10 to the power minus 12 joules. So this is energy after before insertion of the coil. Now we can easily find out what will be the capacitance after the insertion of the coil, after the insertion of the plate, porcelain plate. Capacitance after the insertion of plate. Let us suppose that is C prime, which will be equal to K multiplied by C. K is given to us as 7. 7 into 14 giving us 98 picofarad, or we can say 98 into 10 to the power minus 12 farads. We can charge is going to remain same. Okay, so we have to remember that charge is same. Therefore we can say that energy after the insertion of the plates let us call this as UF will be equal to Q square divided by 2C prime. So we get our UF, charge is same, and charge is our 168 into 10 to the power minus 12 whole square, 2 multiplied by C prime, which is our 98 into 10 to the power minus 12. So we get this energy will be equal to 144 into 10 to the power minus 12 joules. Therefore, we need to find out the mechanical energy gained by because the gain in mechanical energy will be the loss of the energy. So we can say that mechanical energy gained let us call this as delta of U will be equal to over U initial minus U final, and U initial is our 1008 into 10 to the power minus 12 minus 144 into 10 to the power minus 12, and this gives us 864 into 10 to the power minus 12, or we can say 864 picojoules. Energy is 864 picojoules. So this completes the 11 questions for the part 2. Remaining questions from the year 2021 we will try to cover in part 3. If required, we will be doing also part 4, which will be also consisting of advanced questions as and when they are being solved. So this completes part 2 of 11 questions from the year 2021. Thank you.